A conversation between the Archangel Gabriel and the Archangel Michael. Numbered 96. In the name of God, the gracious, the merciful. Read. In the name of your Lord who created man from a clot. Read. And your Lord is the most generous. He who taught by the pen, taught man what he never knew. In fact, man oversteps all bounds. When he considered himself exempt, but to your Lord is the return. Have you seen him who prevents a servant when he prays? Do you think he is upon guidance or advocates righteousness? Do you see how he disbelieved and turned away? Does he not know that God sees? No. If he does not desist, we will drag him by the forelock, a deceitful, sinful forelock. Let him call on his gang. We will call the guards. No, do not obey him, but kneel down and come near. Structure and Functions of the Body. A Handbook of Anatomy by Annette Fisk, AM. The Project Gutenberg e-book of Structure and Functions of the Body by Annette Fisk. This e-book is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. You may copy it, give it away, or reuse it under the terms of the Project Gutenberg license included with this ebook or online at www.gutenberg.org. If you are not located in the United States, you will have to check the laws of the country where you are located before using this ebook. Title: Structure and Functions of the Body, a Handbook of Anatomy and Physiology for Nurses and others desiring a practical knowledge of the subject. Author: Annette Fisk. Release date: March 8, 2021. Ebook number 64,754. Language: English. Character set encoding UTF-8. Produced by MFR and the online distributed proofreading team at https://www.pgdp.net. This file was produced from images generously made available by the Internet Archive. Your reader is Christopher Robert Neal, Doctor of Jurisprudence. Start of the Project Gutenberg ebook Structure and Functions of the Body. An image of a human skeleton posed. The human skeleton, Lewis. Structure and Functions of the Body, a Handbook of Anatomy and Physiology for Nurses and others desiring a practical knowledge of the subject. By Annette Fisk, AM. graduate of the VIII Training School for Nurses, illustrated, Philadelphia and London, W.B. Saunders Company, 1911. Copyright 1911 by W.B. Saunders Company, printed in America. Press of W.B. Saunders Company, Philadelphia. To my father and to Dr. Alfred Worcester, as those who have perhaps most helped me in the formation and realization of my ideals, this book is affectionately dedicated. Preface. Although there are already in existence many books on anatomy and physiology for nurses, none with which I am acquainted has seemed to me to provide in concise form just the knowledge needed by the nurse in her profession. Most of them, moreover, separate the anatomy from the physiology, and all treat the different systems of tissues separately. First the bones, then the muscles, and so on. These defects, as they seem to me, I have attempted to correct, not only by weaving the physiology in with the anatomy, but by treating first the general structures found throughout the body, and then describing the structure and function of each part in detail. Thus, the first chapter is devoted to a description of the general structure of all the tissues. A separate chapter being devoted, however, to the skin, its appendages and function, including the sense of touch. Then the head, with its bones, muscles, and organs of special sense, is described, while the brain is treated with the rest of the nervous system, thus forming the connecting link between the head and the body. In the same way, the back, chest, abdomen, pelvis, and extremities are taken up in turn, and the bones, muscles, blood vessels, nerves, and special organs of each, together with their functions described. Although written more particularly for nurses, I am in hopes that this book may prove useful to any others who may desire to acquire a practical knowledge of anatomy and physiology. Besides the usual textbooks, uh, besides the usual textbooks, I am much indebted for material to notes taken in lecture courses given by Dr. Fred R. Jowett and Dr. F. J. Goodrich of Cambridge, Massachusetts, at the Cambridge School of Nursing, and by Dr. Vivian Daniel of Watertown at the Waltham Training School for Nurses. I wish particularly to express my gratitude and appreciation for the kind and helpful criticism given me by Dr. Eugene A. Darling, Assistant Professor of Physiology, Harvard College, Annette Fisk, May 1911. Contents, Chapter 1, page 11, Composition and General Structure of the Body. Chemical Constitution of the Body, 11, the Cell, 12, the Fundamental Tissues of the Body, 13, Epithelial Tissue, 14, Connective Tissue, 15, Structure of Bone, 17, Bone Formation, 18, Chemical Composition of Bone, 18, Classification and function of bones, 19. Joints, 20. Muscle, 21. Action of the muscles, 23. Physiology of muscle, 24. Cilia, 27. The blood, 27. Arteries, 27. Veins, 28. Capillaries, 28. Lymphatic system, 29. Lymphatic vessels, 31. Lymphatic glands, 32. Lymph, 32. Glands, 35. Ductless glands, 36. Nervous tissue, 36. For this recording, we will take that chapter. Structure and functions of the body. Chapter 1. Composition and general structure of the body. Anatomy is the study of the physical structure, and physiology, the study of the normal functions of the human body. Chemical constitution of the body. In the body, only 20 elements have been found. These include carbon, oxygen, hydrogen, nitrogen, sulfur, phosphorus, calcium, magnesium, manganese, chlorine, potassium, and fluorine. For the most part, they appear in very complex and highly unstable combinations, though oxygen and nitrogen may be said to exist uncombined in the blood. Alimentary canal and lungs. Hydrogen also occurs in simple form in the alimentary canal, but as the result of fermentation, not as an element of the body. Of the organic compounds, some contain nitrogen and some do not. The most important of the former are the proteins, which are found only in living bodies and consist of carbon, hydrogen, oxygen, nitrogen, and sulfur, combined in very similar proportions. The important proteins in the body are serum, albumin, and fibrin found in the blood, myosin in muscle, globulin in the red blood corpuscles, and casein in the milk. Similar to the proteins but capable of passing through membranes are the peptones, the final result of protein digestion, from which the albuminoids differ in that they contain no sulfur. Ferments containing nitrogen exist in all the cells of the body, though more particularly in those of the digestive organs, and the coloring matters, as the bilirubin of the bile, are nitrogenous. The organic substances that do not contain nitrogen are the carbohydrates or starches. The hydrocarbons are fats, and the acids, of which the most important is carbon dioxide, given off by the lungs. The inorganic substances are water, which forms a large percentage of all the tissues, and from 1/4 to 1/3 of the whole body weight. Sodium chloride, or common salt, which plays an important part in keeping substances in solution, potassium and magnesium chloride, and hydrochloric acid found in the stomach. The cell. Although the body is a very complex organism, the cell is its unit or foundation. In fact, the body begins life as a single protoplasmic cell, the ovum, which is frequently compared to the amoeba, a microscopic animal consisting of a single cell of protoplasm or living substance, a substance not well understood as yet, but possessing practically all the functions of the human body. For although it has no organs and is homogeneous in structure, the amoeba can move by throwing out a process and can surround and absorb food, which it builds up into new tissue, discarding the waste. The ovum, however, differs from the amoeba. The ovum, however, differs from the amoeba in that it has a transparent limiting membrane and contains a darker spot, the nucleus. This in turn contains another smaller spot, the nucleolus, while through the protoplasm, which is semi-fluid, extends a fine network that seems to hold it in place. The ovum is very small, about 1/125th inch in diameter, 1/125 inch in diameter, and after fertilization grows by segmentation. The nucleus divides into, and the protoplasm grouping itself anew about the two nuclei. This division continues, each cell dividing and forming two, or sometimes four new cells, all of which at first appear alike. By degrees, however, differentiation takes place and different groups of cells assume different characteristics. Thus, the various tissues are gradually developed, each with a structure and a function of its own, and are distributed among the various organs, each organ consisting of several tissues. During the process of growth and even after full growth of the body is attained, old cells are continually dying and being replaced by new ones. The typical cell is circular, but through being squeezed together in the tissue or for some other reason, the cells vary in shape in different parts, being at times hexagonal. Spindle shapes are columnar, yet whatever their differences in shape or other characteristics, they all live the same sort of life. All protoplasm absorbs oxygen when it comes in contact with it, and in the process of combining with it, is in part burned or oxidized, with the consequent setting free of heat and other forms of energy and the formation of carbon dioxide. So long as the body is alive, therefore, whether it is in a state of activity or of rest, it is the seat of constant chemical change throughout all its cells. And to these chemical changes are due all the forms of energy manifested by the body. For energy is never destroyed, though it may appear in a different form, and the elements of the human body are so combined that their energy may be liberated and manifested in the different functions the body exhibits. The fundamental tissues of the body are the epithelial tissues, the connective tissues, including the cartilaginous and bony tissues, and the muscular and nervous tissues. Of these, the epithelial tissues serve as a protection to the surface of other tissues. The connective tissues together form a framework for the support and general protection of the other tissues. While energy is expended by muscular and nervous tissue, the latter directing the former in its movements. All the tissues are interdependent, and the organs work together. Besides cells, every tissue contains a certain amount of lifeless matter, the intercellular substance, which was at some time produced by the cells. In epithelial tissue, there is little intercellular substance, the cells being close together and arranged generally as a skin or membrane covering external or internal surfaces. When there are several layers of cells, the deepest are columnar in shape, and the others become more and more flattened and scale-like as they approach the surface, where they are gradually rubbed off and replaced by the growth of new cells from below. This stratified epithelium, as it is called, is found wherever a surface is exposed to friction, as in the skin and in the mucous membrane of the mouth, pharynx, and esophagus, and in that of the vagina and the neck of the uterus. In simple epithelium, where there is only a single layer of cells, the cells may be pavement or hexagonal columnar, glandular, or ciliated according to their different functions. The flat pavement cells occur where a very smooth surface is required, as in the heart, lungs, blood vessels, serous cavities, etc. None of these surfaces communicate directly with the external surface of the body, and the name endothelium is substituted for epithelium. The columnar form of cell in the intestine facilitates the passage of leukocytes between the cells. In glandular epithelium, the cells vary according to the gland in which they occur, their protoplasm being filled with the material the gland secretes. Finally, ciliated epithelium is composed of columnar cells, which cilia are little hair-like processes upon their free surface, which serve to send secreted fluids and other matters along the surface where they occur, as in the air passages, parts of the generative organs, the ventricles of the brain, and the central canal of the spinal cord. Connective tissue has a great deal of intercellular substance. One form, areolar tissue, is composed of a loose network of fine white fibers with a few yellow elastic fibers interspersed and with cells lying in the spaces between the fibers. It connects and surrounds the different organs and parts, holding them together, yet allowing free motion, and is one of the most extensively distributed of the tissues. It is continuous throughout. Closely allied to the areolar is the fibrous tissue, in which the white fibers lie close together and run for the most part in one direction only. This is found in ligaments, joints and tendons, as also in such fibrous protective membranes as the periosteum, dura mater, the fasciae of muscles, etc. Fibrous tissue is silvery white in appearance and is very strong and tough, yet pliant. It is not extensile. Elastic tissue, on the other hand, has a large predominance of yellow, elastic fibers and is very extensile and elastic, though not so strong as the fibrous. It is found in the walls of the blood vessels, especially the arteries, in the walls of the air tubes, in the ligaments of the spine, etc. Fatty or adipose tissue is formed by the deposit of fat in the cells of the areolar tissue and is found in most parts where the areolar tissue occurs, though it varies largely in amount in different parts. It is found pretty generally. It is found pretty generally under the skin, fills in inequities or once again. Fatty or adipose tissue is formed by the deposit of fat in the cells of the areolar tissue and is found in most parts where the areolar tissue occurs. Though it varies largely in amount in different parts, it is found pretty generally under the skin, fills in inequalities about various organs and about the joints, and exists in large quantities in the marrow of the long bones. In moderate amounts, it gives grace to the form. In moderate amounts, it gives grace to the form and constitutes an important reserve fund. Cartilage consists of groups of nucleated cells and intercellular substance. It is very firm, yet highly elastic, and serves in the joints to break the force of concussion of the harder and less elastic bones. Except when it occurs at the end of a bone, it is covered with a membrane called the perichondrium, which carries its blood supply. In the nose, ear, larynx, and trachea, it serves to give shape, to keep the passages open, and to afford attachment for muscles. Most of the skeleton of the fetus consists of cartilage, which later develops into bones. Bone. In bone, the intercellular tissue is rendered hard by the deposit of mineral salts, the resulting material being of great strength and rigidity. The texture may be close and dense like ivory, or open and spongy, the difference lying merely in the fact that the one has fewer spaces between the solid particles than the other. There is usually a hard, compact layer on the exterior of the bone, as that is where the greatest cross strain comes, especially in the long bones, while within is the cancellous or spongy tissue. There is usually a hard, compact layer on the exterior of the bone, as that is where the greatest cross strain comes, specifically or especially in the long bones, while within is the cancellous or spongy tissue, which gives lightness to the bone and is capable of withstanding enormous pressure, though it can bear little cross-strain. Structure of bone. The hard substance in bone is always arranged in lamellae, or bundles of bony fibers, which in cancellous tissue meet to form a kind of lattice work, while in the dense tissue they are generally arranged in rings about the Haversian canals, channels through which the blood vessels pass through the bone longitudinally, longitudinally. Structure of bone. The hard substance in bone is always arranged in lamellae, or bundles of bony fibers, which is cancellous tissue, which in cancellous tissue meet to form a kind of lattice work, while in the dense tissue they are generally arranged in rings about the Haversian canals, channels through which the blood vessels pass through the bone longitudinally. Between the lamellae are spaces called lacunae, in which lie branched cells, the spaces being connected with each other and with the Haversian canals by numerous tiny canals, or canaliculi, by which nutrient materials finds its way from the Haversian canals to all parts of the bone. Within the bone is the medulla, or marrow, which is of two varieties: the yellow, which is largely fat and is found in the long bones of adults, and the red, which is nearly three-fourths water and is found in most of the other adult bones and in the bones of the fetus and of the infant. Lining the medullary and cancellous cavities is a delicate connective tissue lining, the endosteum, which contains many bone-forming cells, while on the outside of the bone, except at the articular ends, is the periosteum, with its outer protective layer and its inner vascular layer containing osteoblasts, or bone-forming cells. The periosteum is essential for the growth of new bone where the old bone has died, and if the periosteum is removed from healthy bone, the part beneath is liable to die, as it is by the constant growth of the osteoblasts that the bone grows and is renewed. In the repair of broken bones, tissue is formed between and around the broken ends. Bone formation. Most of the skull and face bones begin as membranes of connective tissue, that is, are formed in membrane. Bones are also formed in cartilage. The bone formation, in this case, beginning from centers of ossification, where the deposit of lime salts in the intercellular substance begins. The salts coming to the centers dissolved in the plasma. Such a center of growth in a bone is called the epiphysis and is separated from the main part of the bone, or diaphysis, by cartilage until full growth is attained. When ossification becomes complete, so in surgery, in working on the bones of children, part of the epiphysis should always be left for the sake of future growth. The outer shell of compact tissue is deposited by the periosteum. Chemical composition of bone. Chemically, bone is composed of about one-third organic or animal matter, largely gelatine, and two-thirds inorganic matter, including various salts of calcium, magnesium, and sodium. In young children, the animal matter predominates and the bones are soft and often bend instead of breaking, only the outside shell on one side giving way, as in green stick fracture. In rickets, there is a deficiency of lime salts, but the increased brittleness of the bones in old age is due not to increase of mineral matter, but to the less spongy texture of old bones. Classification and function of bones. There are in the body some 200 bones, which may be classified as long, short, flat, and irregular. Occasionally, an irregular bone develops in a fontanelle, the membranous opening at the juncture of the sutures of the skull. This is known as a Wormian bone. It is not, however, included in the 200, as are not the sesamoid bones or bones developed in tendons, with the exception of the patella or kneecap. Long bones are developed in cartilage and consist of a shaft, two extremities, and various processes. They are more or less curved to give them strength and grace. They serve as supports and act as levers for purposes of motion and the exercise of power. Since a hollow cylinder is just as strong as a solid one of the same size, the weight coming only from the outer shell, the great bones which are accountable for weight, and which need to be light themselves have hollow shafts, composed chiefly of compact tissue with a central medullary canal. The ends, however, are expanded in order to make better connection at the joints and to afford broad surfaces for muscular attachment, cancellous tissue being used in them for lightness and strength. The large spongy ends also give elasticity and lessen jar, and by bringing the tendons to the bone at a greater angle increase their effectiveness. Blood is brought to the long bones not only by the vessels of the periosteum, but by the medullary artery, which penetrates the compact tissue by the nutrient foramen and divides into an ascending and a descending branch. Short bones are spongy throughout. They are used for strength and where little motion is required. Flat bones are composed of two thin layers of compact tissue with a varying amount of cancellous tissue between and are for protection and muscular attachment. The cancellous material between the two layers or tablets of the skull is called the diplo. Eminences and depressions occur on bones, and when they are not articular, are for the attachment of ligaments and muscles. If they are articular, they help to form joints. As a whole, the bony framework serves to keep the soft parts in place, to support and protect them, and to aid in locomotion. The bones of the head and trunk support and protect organs. Those of the arms are for tact and prehension. Those of the lower extremities are for support and locomotion. Normally, bones have little sensibility, but when inflamed, they are extremely sensitive and painful. Joints. Joints. The bones are connected and move upon one another by means of joints. These joints are of three kinds. Number one, immovable, where the adjacent margins of the bones are closely applied with little fibrous tissue between, as in the sutures of the head. Number two, those with limited motion, which are very strong, the parts being connected with tough fibrocartilage. And number three, freely movable. In this last group, the articulating surfaces are covered with cartilage, which again is lined with a delicate synovial membrane, which secretes a small amount of lubricating fluid. The synovial fluid to reduce friction. Their surfaces are also sometimes deepened by the presence of interarticular fibrocartilages. Bursae, or sacs of synovial membrane, occur outside the joints under tendons and ligaments to reduce friction. The nature and extent of the motion of a joint is defined, and the bones are held together by strong bands of fibrous tissue or ligaments, these ligaments being more fully developed in joints where there is great freedom of motion or where there is great weight to be supported. In a ball and socket joint, such as the hip, there is a ligament in the form of a strong capsule which surrounds the joint on all sides and limits its motion. While hinge joints like the elbow and pivot joints such as that formed by the atlas of the axis have literal ligaments that allow of freer motion. In the shoulder joint, which is the most freely movable joint in the body, the capsular ligament is very lax. In general, the kinds of motion possible in joints may be said to be flexion, extension, abduction, adduction, circumduction, and rotation. When much violence is applied to a joint and no dislocation results, as in a sprain, there is often much stretching and even laceration of the ligaments. Muscle. The flesh, which forms a large proportion of the weight of the body, consists of muscular tissue. Of this two kinds are found: the striated or stripped muscle of animal life, which is under the control of the will and so is known as voluntary muscle, and two, the unstripped or smooth muscle of organic life over which we have no control. That is, the involuntary muscle. Each fiber of stripped or striped muscle has an elastic, membranous sheath, the sarcolemma, and consists of rod-shaped cells with a nucleus along the edge, set end to end and having cross-wire striations. In unstriated muscle, the fibers, which have no sarcolemma, consist of oval or spindle-shaped cells, with a nucleus much smaller than that of stripped muscle and situated in the middle. In both kinds of muscle, the fibers are bound together with connective tissue and blood vessels into fasciculae or bundles. and many bundles go to make up a muscle. The muscle, in turn, has a connective tissue envelope or sheath, the fascia. These fasciae are found throughout the body, the superficial ones being just beneath the skin, while the deep ones not only form sheaths for the various muscles, but form partitions between them and serve to strengthen their attachments. The striped muscles are those of motion, while the unstriped occur in the hollow organs surrounding the cavity, and in some cases lessening its capacity by their constriction. An intermediate form of muscle, known as cardiac muscle, occurs in the heart. Here the fibers have striations, but the nucleus is generally in the middle of the cell, and the fibers branch and run together. In life, muscle appears more or less translucent and is contractile and alkaline, but in death it loses its translucency and becomes rigid, at the same time giving off in decomposition much carbon dioxide so that its reaction is acid. This phenomenon of the muscles becoming rigid in death is called rigor mortis and occurs generally a few hours after death, though it may come at once or be considerably delayed. It may last anywhere from a few moments to several days, but generally lasts from 24 to 36 hours. It is probably due to the formation in the muscle of myosin, a substance which probably comes from myosinogen in the living muscle and which is closely akin to the fibrin of blood. Probably the myosin, or what precedes it, causes clotting of the muscle just as fibrin, or what precedes it, causes clotting of the blood. The muscles vary in shape in different parts of the body, being long and slender in the limbs, and broad and flat in the trunk. They are attached chiefly to bones, but also to cartilages, ligaments, and skin, either by means of tendons, which are cords or bands of white, inelastic, fibrous tissue, or by means of aponeuroses, membranous expansions of the same nature. Most voluntary muscles consist of a belly, and two ends are tendons. The origin is the fixed point from which it acts, while the movable point upon which it acts is known as its insertion. Action of the muscles. When attached to bones, muscles are distributed in three ways. 1. When it is necessary to produce much motion rapidly, a short muscle is used. Number 2. When a part needed to be moved far and much contraction on the part of the muscle is, therefore, needed, the muscle is very long, as in the case of the sartorius muscle, which shortens half its length. Finally, where less distance has to be covered, but greater power is required, tendons are used, as in this case the contraction is powerful, but does not carry that part far. In performing the mechanical work of the body, The muscles are aided by the fact that the bones, to which they are largely attached, are set together loosely and form a set of levers on which the muscles act to perform certain definite acts. All three classes of levers occur, where the fulcrum is between the weight and the power, as in the case of the head, which is balanced by the muscles of the neck on the vertebrae. Number two, where the weight is between the fulcrum and the power, as when a person raises himself upon his toes. And number three, where the power is between the fulcrum and the weight, as when the biceps is used to raise a number three, where the power is between the fulcrum and the weight, as when the biceps is used to raise a weight held in the hand. The erect position of the body is difficult to maintain because the center of gravity is high. And it is by the contraction of many muscles in the legs, thighs, back, abdomen, and neck that the body is balanced upright upon the feet. Physiology of muscle, irritability or sensitiveness to stimulation, and contractility or the power to contract are the two most important functions of muscle. Contraction occurs in response to nervous energy brought by the nerves, a nerve filament going to each muscle fiber into which it plunges, its substance being lost and its sheath becoming continuous with that of the muscle fiber. Any irritant, as heat, electricity, etc., when applied to the nerve, causes the muscle to contract. Moreover, muscle has an irritability of its own and can contract independently of the nervous system. In contracting, it shortens and thickens, bringing the two ends closer together, and becomes firm and rigid. The amount of contraction depends upon the strength of the stimulus and the irritability of the muscle. The minimal stimulus is the least stimulus that will cause a contraction, and the maximal is one that will cause the greatest contraction. The work done depends in like manner upon the strength of the stimulus. During contraction, certain sounds are given off called muscle sounds, which can be heard with the stethoscope but have no special significance. The muscles which have the greatest power of rapid contraction are generally attached to levers. Indeed, striated muscle is characterized by the rapidity and strength with which it works, though its rhythmic motion is slight. Smooth muscle, on the other hand, is characterized by its great force, considerable rhythm, considerable tone, and slight rapidity. That is, its contraction is slower and lasts longer than that of striated muscle. Cardiac muscle is characterized by great rhythm and force, fair rapidity, and slight tonicity, tonicity being the amount of tone or readiness to work. For even in sleep, muscle is always in tone, that is, ready to do its work. It is this that makes the difference in appearance between a living and a dead person. It enables one to spring to his feet at time if he hears a noise, a thing he could not do if his muscles were wholly relaxed. Thus, rapidity is the great function of striated, tonicity of smooth, and rhythm of cardiac muscle. In paralysis, the muscles droop and lose their tone. Muscles are frequently the seat of rheumatic disorders. When set free, potential energy accomplishes work. In muscle, there is a great deal of potential energy, which is set free as heat and as work accomplished. Even when the muscles are at rest, chemical changes are going on and heat is being produced. Though more heat is produced when they are functioning, if the body depended upon its gross motions for all its heat, it would grow cold while a person rested. The respiratory organs, however, and the heart are always working, and chemical changes are constantly taking place. Ordinarily, a muscle has some object in contracting, such as the raising of a load, and it contracts voluntarily more or less according to the weight of the load. The amount of work done is calculated in foot-pounds or gram-meters, that is, the energy required to raise 1 pound, 1 foot, or 1 gram, 1 meter. As a rule, the muscles with the longest fibers, as the biceps, do the most work, and those with a large number of fibers do more than those with less. It has been calculated that whereas an engine gives back 1/12 of the energy of the coal consumed, muscle liberates 1/4 of the energy brought to it in the form of food. During activity, the glycogen, or sugar in the muscle, is used up and the muscle becomes more acid, owing to the lactic acid that is formed. The carbon is taken in and carbon dioxide given off. Nitrogen puts the muscle in condition to do its work, but is not so much used up in the work as in the carbohydrate material. So it is the non-nitrogenous matter that does the work, and any increase of urea, the end product of protein metabolism, is mere wear and tear. Sudden heat or cold causes muscular contraction, and moderate heat favors both muscle and nervous irritability. Moderate cold, however, lessens the force of contraction, and below zero muscle very largely loses its irritability without necessarily becoming rigid. While well supplied with blood, muscle will contract without fatigue. But if the blood supply is shut off, it soon loses its irritability and becomes rigid. The more a muscle is used in moderation, the more it develops. But after it has done a certain amount of work, it becomes exhausted, losing its irritability or power to respond to stimuli, and later becoming rigid. Such fatigue is due to the production of certain poisonous waste products, which have a paralyzing effect on the nerves and which are ordinarily gradually carried away in the blood, but which sometimes, if produced to excess, accumulate too fast for the blood wholly to remain. If produced to excess, again, such fatigue is due to the production of certain poisonous waste products which have a paralyzing effect on the nerves and which are ordinarily gradually carried away in the blood, but which sometimes, if produced to excess, accumulate too fast for the blood wholly to remove them. Usually, the nerve becomes exhausted first and the muscle substance later. So long as it is connected with the nervous system, a muscle will respond to stimuli, But when the nerve becomes tired, degeneration is more rapid. In fact, the degree of exhaustion is determined by several factors, as by relation to the central nervous system, variations in temperature, blood supply, and functional activity, the process being more rapid in warm than in cold-blooded animals. Cilia, Cilia. A few motions are accomplished by tissue that is not muscular, as in the case of the cilia attached to the cells of the respiratory tract, which lie flat on the free surface and then lash forward, serving in the air cells to keep the air in motion, and in the tubes to send secretions from below upward and outward and to keep out foreign bodies. Cilia are also found in the female genital tract, where they aid the passage of the ovum from the ovary to the womb. They act together, though apparently not governed by the nervous system, as in the white corpuscles of the blood, whose motion also is not muscular. The changes that take place in ciliated epithelium are probably about the same as those in muscular tissue, that is, contractile. The blood. To most of the tissues just described, nourishment is brought in the blood, which circulates through the body in a system of hollow tubes, the arteries and veins, whence it is distributed through the agency of the lymphatic system. There are no blood vessels, however, in the epidermis, epithelium, nails, hair, teeth, nor in the cornea of the eye. The vessels that carry the blood from the heart are called arteries. Those that return it, veins. The former begin as large vessels and gradually decrease in size. The latter begin as small vessels and form larger and larger trunks as they approach the heart. The arteries have three coats. Number one, a thin serous coat. The internal or intima. Number two, a middle or muscular coat. And number three, an external coat of connective tissue. The middle coat is the thickest and is the one that prevents the walls from collapsing when cut across. Except in the cranium, each artery is enclosed in a sheath with its vein or veins, the venae cometes. Usually the arteries occupy protected situations and are straight in their course, where a vessel has to accommodate itself to the movements of a part. However, it may be curved, as in the case of the facial artery, which is curled on itself to allow for movement of the jaw. They anastomos, or communicate freely with one another, thus promoting equality of distribution and pressure and making good circulation possible even after the obliteration of a large vessel. The veins have three coats, like the arteries, but they are not so thick, and the muscular coat is not so highly developed. so that the walls collapse when cut and have no elasticity. There are constrictions on the surface of many of the veins due to the presence of valves. These valves are formed of semilunar folds of the lining membrane and are arranged in pairs. They serve to prevent the blood, whose circulation in the veins is sluggish, from flowing back. There are two sets of veins, the superficial and the deep, which communicate with each other. In fact, all the veins, large and small, anastomose, vary freely, especially in the skull and neck, where obstruction would result in serious trouble throughout the spinal cord and in the abdomen and pelvis. The deep veins accompany the arteries in their sheath, while the superficial ones have thicker walls and run between the layers of the superficial fascia under the skin, terminating in the deep veins. In the skull, the venous channels take the form of sinuses formed by a separating of the layers of the dura mater, or dura mater, with an endothelial lining that is continuous with that of the vein. In the skull, the venous channels take the form of sinuses formed by a separating of the layers of the dura mater with an endothelial lining that is continuous with that of the veins. The capillaries are intermediate. The capillaries, Capillaries, are intermediate between the arteries and the veins, the final division of the arteries and the first source of the veins. They are tiny vessels with but a single coat, continuous with the innermost coat of both arteries and veins and consisting practically of one layer of cells with a small amount of connective tissue between. They spread in a great network throughout the tissues, forming plexus or plexuses, Plexusex, and being especially abundant where the blood is needed for other purposes than local nutrition, as in the secreting glands. Their diameter is so small that the red corpuscles have to pass in single file and may even then be squeezed out of shape, as they have no muscle tissue in their walls. They have no power of contracting. Their walls, however, like those of the smaller arteries and veins, are porous, and by virtue of this quality, they play an important part in the economy, since in them the exchange takes place between the tissues and the blood. The arteries in general carry freshly oxidized blood, and the veins blood from which the oxygen has been largely used up and which contains waste material. In the pulmonary system, however, the case is reversed. The pulmonary arteries conveying venous blood, as it is called, from the heart to the lungs to be oxidized, and the veins returning the blood after it has received its new supply of oxygen. The pumping of the blood through the arteries is assisted by the contraction of the muscular coat, while the elastic tissue, of which it contains a certain amount, gives elasticity to the walls and enables them to stretch and so to accommodate the larger blood supply forced into them at each beat by the heart. The walls of the veins have not the power of contracting, and the blood is pushed through more by gravity and the action of the arteries than by any action of their own. The walls of all the vessels are nourished by tiny blood vessels in the outer coat, known as vasa vasorum, and the nerves that regulate the action of the arteries are the vasomotor nerves from the vasomotor center in the medulla. Sufficient impulse goes from this center to the blood vessels all the time to keep them somewhat contracted in a state of tone, that is, which is increased or diminished as the blood supply is to be diminished or increased. Lymphatic system. The lymphatic system also extends throughout the body and consists of a system of channels, spaces, and glands very closely related to the circulatory system and contains a fluid called lymph. There are three principal parts of the system. Number one, the lymph spaces, which are open spaces with no definite walls in the connective tissue framework of the body, more frequent near arteries and veins, and especially so among the capillaries. Number two, the lymph capillaries, or small vessels which connect the lymph spaces, and number three, the lymphatic vessels, of which is a deep and superficial set, the latter accompanying the superficial veins of the surface of the body, the former accompanying the deep blood vessels. The lymph spaces are generally small, though there are some large serous cavities, such as the abdomen, that may be considered an extended lymph space. The lymphatic vessels have delicate, transparent walls with three coats like the arteries, though much thinner, and anastomos even more freely than the veins. They have a beaded appearance due to the presence of numerous valves, which form constrictions on their surface. The right lymphatic duct, which is only about an inch long, drains all the lymphatics of the right half of the upper part of the trunk, the head, and the neck approximately, while the thoracic duct drains those of the rest of the body. The latter, which is the largest vessel of the system, begins opposite the second lumbar vertebra with a bulb-like reservoir for the lymph or chyle, the receptaculum chyle, and extends up along the spinal column for a distance of about 18 inches to the seventh cervical vertebra, where with the right lymphatic duct it empties into the left subclavian vein at its junction with the internal jugular, thus establishing direct communication between the lymph spaces and the venous system. The orifices of both vessels are guarded by semilunar valves to prevent regurgitation of the blood. The lymphatic glands are small oval glandular bodies and occur here and there along the course of the lymphatics. Before entering one of them, the vessel breaks up into several different vessels, which form a plexus within and then emerge again as several efferent vessels, which soon unite to form one trunk. These glands occur chiefly in the mesentery, along the great vessels, and in the mediastinum, axilla, neck, elbow, groin, and popliteal. Once again, these glands occur chiefly in the mesentery, along the great vessels, and in the mediastinum, axilla, neck, elbow, groin, and popliteal space. The lymph varies in character, with the locality being a little thicker and more opalescent in the lacteals, as the lymphatics of the small intestine are called, especially during digestion when fat is present. Here it is called chyle, otherwise it is generally a clear, transparent, and slightly opalescent fluid, which, owing to the presence of fibrin, clots when drawn from the body and allowed to stand. In fact, it resembles blood plasma very closely in composition, and as it also contains a certain number of corpuscles or leukocytes that just correspond to the white corpuscles of the blood, it is practically blood without the red corpuscles. These leukocytes have considerable power of amoeboid movement and are thought by some to play an important part in the absorption of food. Owing to intracapillary pressure, the lymph transsudes into the lymph spaces and bathes the tissues, being carried away again by the lymphatics. The amount of transudation is determined by the blood pressure. The greater the pressure, the greater the amount of transudation, and is increased by some organic action of the cells in the walls of the vessels. In the process of transudation, a certain amount of solid matter goes through the wall of the vessel, and it is probable that certain protein elements can be carried thus from the blood vessels to the lymphatics, though they do not pass through the capillary wall as readily as the substances. Some lymph is also probably formed by the action of the tissues themselves, though the process is not understood. All muscular movements, active or passive, including the respiratory movements, tend to drive the lymphs on its way by pressure, the valves of the vessels keeping it from flowing back. Moreover, its flow is from the capillaries to the veins, or from a region of high pressure to one of less pressure. There is probably also some contraction in the walls of the vessels themselves, and the continual formation of lymph helps to drive it along. If an obstruction to the circulation occurs, however, back pressure results and causes too great transudation. In that event, a limb becomes swollen, pale, and generally cool. It pits on pressure, the pressure driving the lymph out and there being no circulation to bring it back. This condition is called oedema and occurs in liver, kidney, and heart troubles. being generally first observed at the ankles in ascites, hydrothorax, hydrocephalus, and pericardia, and pleural effusions. The fluid corresponds to lymphs in its composition, and the large amount is due to excessive formation of the fluid, which is normally present in small quantities. If an obstruction to the circulation occurs, however, back pressure results and causes too great transudation. In that event, a limb becomes swollen, pale, and generally cool. It's, it pits on pressure, the pressure driving the lymph out, and there being no circulation to bring it back. This condition is called oedema and occurs in liver, kidney, and heart troubles, being generally first observed at the ankles, in ascites, hydrothorax, hydrocephalus, and pericardia, and pleural effusions. The fluid corresponds to lymph in its composition, and the large amount is due to excessive formation of the fluid, which is normally present in small quantities. Lymph gives the tissue substances from the blood that they need and carries off those they do not, whether waste or substances of use, to other tissues, because they thus absorb certain materials not needed in the tissues and convey them to the circulation. The lymphatics have also been called absorbents. Indeed, lymph may be spoken of as the middleman between the blood and the tissues. Another function of the lymph is to lubricate. Thus, the synovial fluid of the joints is lymph, and the pleurae and the pericardium contain lymph or serum to reduce the friction between the adjoining surfaces as much as possible. The brain and spinal cord do not quite fill the cavities of the cranium and the spinal column, but float on a cushion of lymph. The cerebrospinal fluid, when the brain, which is subject to increase and diminution in size, increases in size, it drives the lymph out, and when it diminishes, the lymph returns. The lymph glands serve as a protection to adjacent parts, and when it leaves the gland, the lymph is purer and richer in leukocytes than when it entered. In fact, they filter harmful matter from the lymph and apparently also form white corpuscles. Normally, they can with difficulty be felt in disease. If the leukocytes are unable to destroy or carry off the poison, the lymph carries it along to the glands, which swell and become tender. If the infection is not severe, the swelling goes down and the tenderness passes after a short time. But if it is severe, there may be suppuration and abscess formation, and the gland even perhaps be destroyed, giving its life for the health of the part. Thus, a wound in the foot, if infected, may cause irritation and enlargement of the glands at the knee and in the groin. The lymphatic glands are frequently the seat of tubercular infection tubercular infection, especially in the neck, and are enlarged in scarlet fever, tonsillitis, and diphtheria. In syphilis, there is general glandular enlargement, and the glands in the groin become enlarged in all diseases of the genital organs. In malignant growths, such as cancer, the extension of the disease is often along the lines of the lymphatics. Glands. Of glands, in general, a word might now be spoken. They are of two kinds, excreting and secreting, and when simple, are formed by the folding in of a free surface, as in the case of the salivary, gastric, and sebaceous glands. The cells at the gland become so modified as to be able to perform the function of excreting or secreting. In racemose glands, the gland is broken up into many pockets. Excreting glands take from an organ or from a part substances which have outlived their usefulness and are to be cast out of the body, while the secreting glands form from the blood substances that did not exist in it before, but which are of use to the body, as the Ptyalin, Ptyalin of the saliva. A strict line cannot, however, be drawn between the two kinds of glands. Most glands partaking more or less of both functions, though the sebaceous and sweat glands are probably purely excreting glands, and the salivary glands are almost purely secreting. The glands, moreover, are more or less interchangeable in their functions, that is, they have vicarious function, and one gland can take up and do for another what that other is for some reason unable to do. In jaundice, where there is stoppage of the bile duct, the kidneys help out the liver by excreting the bile. If one kidney is removed, the other does work for both, and the glands of the skin may help out the kidneys or vice versa. Hemorrhage from the lungs sometimes occurs in suppression of the menses. In general, in a general way, the function of glands is chemical. They filter out by osmosis, selecting the useful parts for secretion and the useless for excretion. In the chemical action that goes on, considerable energy is given off, as is shown by the amount of pressure in the glands and by the fact that their temperature is higher than that of the blood. They all work in a reflex manner, being under the control of the central nervous system. Thus, what is eaten affects the nerve terminals in the mouth. The sensation passes to the nervous system, and an impulse is carried by the motor nerves to the salivary glands. Most of the glands have ducts to convey away their secretion to other parts of the body or to send excretion out of the body. But there are also ductless glands, which, though they seem to have some important function in the process of metabolism, are not well understood. Most of them seem to manufacture some substance that is absorbed by the tissues and that plays an important part in the bodily metabolism, though nothing is secreted by them externally. They are said to have an internal secretion, whereas the glands with ducts have an external secretion. The liver has both forms of secretion, the bile which is sent out and the glycogen which is stored. The ductless glands are the thymus and thyroid glands, the suprarenal capsules, and the pituitary body and the brain. Nervous tissue, presiding over all the organs, muscles, and blood vessels, as the source of all action and sensation are the nerves. Nervous tissue is of two kinds. Number one, the gray are vesicular, which originates impulses and receives impressions, and number two, the white are fibrous, which conveys impressions. The gray matter consists of large granular cells of protoplasm containing nuclei, which give off many branches and dendrites. From the undersurface there usually comes one main branch, the axis cylinder process. These processes sometimes give off branches and sometimes not, but they form the nerve fibers and carry impulses away from the nerve cells. The cells of the processes are elongated in shape, have a nucleus, and are placed end to end with a definite constriction between them. Each axis cylinder process is surrounded by a sheath called the medullary sheath, while each nerve fiber consists of a central axis cylinder process surrounded by the white substance of Schwann and enclosed in a sheath. A bundle of these fibers invested in a fibroareolar membrane called the neurilemma constitutes a nerve. A bundle of these fibers invested in a fibroareolar membrane called the neurilemma constitutes a nerve, and of these the white matter is formed. The blood supply is brought by minute vessels, the vasa nervorum. The nerves of the cerebral spinal system preside over animal life and have to do with voluntary acts, while those from the sympathetic system regulate organic life and are quite independent of the will. The nerves of the cerebral spinal system preside over animal life and have to do with voluntary acts, while those from the sympathetic system regulate organic life and are quite independent of the will. Both sensory and motor nerves extend all over the body, accompanying the arteries in a general way. The sensory nerves end on the surface in plexuses, in end bulbs situated in the papillae of the skin, or in tactile corpuscles, these last occurring more especially where there is no hair. The motor nerves and peripherally The motor nerves end peripherally in plexus. The motor nerves end peripherally in plexuses or by end plates. The central terminations of the motor nerves and the terminations of sensory nerves in special organs, except where they end in a cell, are not well understood. Like muscles, nerves are probably never at rest, for through them the muscles get their tone. When a nerve acts, no heat is produced, and there is no change in the nerve afterward, as there is in muscle. Probably nerve impulse is the transmission of physical rather than chemical changes along the fiber, the atoms of the nerve being set in vibration, and the vibrations being transmitted along its length. Stimulation is produced by physical injury, by chemical influence, by electricity, by heat, and the message is always referred to the nerve termination. Thus, If the nerve at the elbow over the crazy bone is touched, a tingling is felt in the fingers rather than at the pressure point. A person who has had an arm or leg amputated will frequently speak of this. A person who has had an arm or leg amputated will frequently speak of his fingers or toes on that side being cold or complain of pain in them because the scar below the point of amputation tightens around the nerves and pinches them. It is through the nerves that people get in touch with the outer world and that they judge of size, weight, etc. All careful adjustments of the muscles and under the control of the nervous system. Once again, if you touch your elbow, you'll feel it in your fingers. So to feel with your fingers, your elbow is enough. End of chapter 1. Chapter 2 begins the skin, its appendages, and its function.